Hi everyone, we'll just give it a network. Welcome to our webinar titled Applying the Watershed Protection Standard to Stormwater Control System Design, featuring our speaker James Houle, Director of the UNH Stormwater Center. The purpose of the SNP Network webinar series is to showcase the work of our partners and share our regional case studies and emerging topics and resources relevant to the SNP region. We are grateful to have this opportunity to share this important work with the communities in this region. My name is Leah Soloway. I'm the SNP Network Program Coordinator located at the New England Environmental Finance Center, and I'll be managing logistics for today's program. Before we get started, I'd like to introduce and provide you all with a little background about the SNP Network and the SNP region. The SNP Network is a technical assistance and training program that is led by the New England Environmental Finance Center, which is a regional technical assistance provider for EPA Region 1. The SNP Network's mission is to empower communities to achieve healthy watersheds, sustainable financing, and long-term climate resilience through the management of stormwater and restoration projects. We focus on building local capacity by providing no-cost trainings, webinars, and hands-on technical assistance to communities in the SNP region. The SNP Network is funded by the Southeast New England Program Network, or SNP, which is a bi-state initiative of EPA Region 1 that supports clean water, healthy ecosystems, and sustainable communities across Southeast Massachusetts and Rhode Island. If you'd like to learn more, please visit our website, snpnetwork.org. And before we begin the webinar, there are a few logistics to keep in mind. First, everyone will be on mute to ensure audio quality. At the end of the webinar, there'll be a Q&A section. This will be an opportunity to ask questions by typing them into the Q&A box on your Zoom control panel. We look forward to answering questions, so please type them in at any time during the webinar. And this webinar is being recorded, and the recording, along with associated materials, will be sent to the participants and available on our website. Today, you'll be hearing about the Watershed Protection Standard Toolkit, a resource that was funded and brought to fruition by the SNP Network. The SNP Network partners saw a need to translate EPA's research of the Watershed Protection Standard into digestible materials that are understandable and accessible to a wide audience. The SNP Network hired VHB to lead the development of this resource alongside SNP Network partner UNH Stormwater Center, Roca Communications, and the SNP Network's Low Impact Development and Nature-Based Solutions team to serve as the advisory group for this project. And this toolkit was completed in the fall of 2025. And with that, I'd like to introduce SNP Network partner James Houle of the UNH Stormwater Center. I will now hand things over to Jamie, and I'll stop sharing, and Jamie, you can go ahead and share.
Great. Thank you, Lena. I think I pushed share too early. All right. I think we're rolling. Welcome, everybody. It's a pleasure to be here to talk about the Watershed Protection Standard. And I think we build this webinar as a deeper dive into some of the more technical aspects of implementation. So while I love to talk about it, I'm not really going to cover a lot of the background. Hopefully, you can get that from the SNP Network. I think we have a previously recorded webinar if you want to know about the Taunton study in the background. So it's an opportunity to dig more into the technical aspects of the Watershed Protection Standard and how to actually help implement it. So there's on the technical side, there's for me, a lot of exciting things. We're ushering in a new era, really, on regulations by accessing and utilizing the continuous simulation modeling that was done for the Taunton study, and we're implementing that into accessible tools that are improving the way we engineer these systems. So I appreciate Leah covering the project partners. This was done by the SNP Network. The Southeast New England program is an regional environmental program at EPA Region 1. And it's administered by the University of Southern Maine and the New England Environmental Finance Center. We hired VHB, and it was really great to work with VHB. And as you'll see, they were really they kind of pushed the implementation aspects of the watershed protection forward. So it's always good, you come up with the science is sometimes the easy part. So having a partner like VHB that really helps us on the implementation side is a critical component. So we really value the partnerships that the SNP Network uh, really brings together. Um, and of course, working with Roca Communications means that our communication products are really top notch. I've been working with Dolores Leonard for a while at Roca Communications, and I can't uh, stress enough the value that communications expertise brings to this type of process. So you can thank her for the if you find these materials easily communicated, and you can thank VHB and Dolores. Of course, just very simply, the background around the watershed protection standard is because in this area, I mean, it's a blessing and a curse, but we have a lot of water. There's a lot of talk right now about water reuse. It really is not that applicable here. Water reuse we look at as infiltrating stormwater, and really that's what the watershed protection standard is all about. Not necessarily reusing it. From a surface water perspective, but putting it back into the ground where it's naturally filtrated and um, gets back to the streams as cool and clean base flow. So we need management because we have too much water. And sometimes we have, with climate change, we have periods of not enough water and drought. So again, another reason why infiltrating water back into the ground is the best way to really deal with some of these challenges that are likely only going to increase as we move into the future. And then, of course, everything is largely driven by water quality and the Clean Water Act. So the target here is no net release of especially nutrients. And nutrients are kind of the challenging resource, at least in New England. So it's phosphorus or nitrogen or both. So that's really challenged the engineering behind stormwater management systems, and it really requires us to improve our game from a treatment strategy. We're hoping that you agree at the end of this that access to better science, better modeling, and better strategies and approaches that we make this not only achievable, but very cost effective from an implementation perspective. And hopefully fair as well as we're trying to, on the development side, we're trying to make sure that the development is not adding or causing or contributing to water quality impairments. And we're trying to also access and harness the power of redevelopment to build resiliency when we develop. And we do that through regulations. And so, if you think about it, this is the lowest cost control that can actually be imparted. It doesn't cost much from the implementation perspective from a municipality. It does require more engineering around stormwater controls, but we know that's where we're going anyway. Right now, our infrastructure is challenged. It was built decades. It's decades old at least, and was built for a precipitation regime that is changed. So, our infrastructure that we're discharging to is already vulnerable. And so this is the best approach to increase resiliency in the landscape. Just to give you an idea, we're still looking for the first to adopt communities to adopt the watershed protection standard. There's technical assistance that's out there, whether it's through the network or through the water TA program through NewWin, and we'll talk more about opportunities to engage with those partners later. But it has been implemented, at least in the guidance of the updated New Hampshire Stormwater Manual. So while New Hampshire's not in the SNEP region, we're still in New England, and I feel like a lot of the regulations and implementation strategies are kind of converging around New England. So whether you're in Massachusetts or Rhode Island or New Hampshire or Vermont or Connecticut or Maine, a lot of these you're going. Hopefully, the watershed protection standard is not going to be a novel thing over the next decade. So the way it was implemented in New Hampshire is it's kind of a sequential selection. So we're always promoting step one, which is better site design. So some places call this environmental site design. Some people call it low impact development design. Some areas it's called sustainable site design. Whatever the case, it's smart design. It emphasizes pre-development hydrology, honoring pre-development sub-drainage areas so that you're not starving wetlands or overwhelming infrastructure by completely changing the hydrology on site. This is tough to regulate, but it's always something that we try to promote. And we see more and more adoption as we're moving forward. Smart or better site design or environmental site design or LID is a really smart thing to be able to offer to development clients. The next step is the Watershed Protection Standard. So it's really a retention standard such that you're designing stormwater control measures so it yields no net increase in nutrient discharge, right? So that is the Watershed Protection Standard. It's roughly equivalent to a 1-inch on-site retention, but it's obviously dependent on soil types and the types of stormwater control measures that you're using. And we'll dig into that as we go along. If for some reason you cannot meet an on-site retention requirement, maybe there's it's areas of high potential pollutant load like gas stations or industrial facilities. Maybe it's in areas where you shouldn't be infiltrating because there's high groundwater or shallow bedrock. Then we're moving to this treatment standard, a 90% TSS reduction, a 60% phosphorus reduction, and a 50% total nitrogen reduction. Beyond that, we are recommending other requirements. Maybe so there's not a get out of jail free card. If you can't do anything on site, there's potential for offsite meeting those targets offsite as well within the same watershed. A lot of this information is detailed in, again, the New Hampshire Stormwater Manual, and it's also reflected in the Watershed Protection Toolkit, where we have templates for adopting local regulations. And we're not going to cover that today, but maybe that's an area of topic, not necessarily an area of my expertise, but more of a planning, how to translate the regulatory language into site plan review documents and the overall ordinances that our community regulates development from. Sorry, there's the QR code for the New Hampshire Stormwater Manual if you want to take a look and see how we're implementing it. So this is the toolkit. So I think Leah dropped the link in the chat or provided the QR code at the beginning. This is what you'll find if you go to the SNET Network website and click on the Watershed Protection Standard Toolkit. So see, we have fact sheets, promotional handouts. There's the template for regulatory language. What we're going to focus on today are the site examples and the Watershed Protection Standard calculator. Those are tools that are available that will allow you to meet the requirements in the most efficient and effective way. So the first thing I want to start to go through are these design templates. So VHB spent a lot of time and looked at a number of different land use scenarios and provided templates on how you could meet the Watershed Protection Standard across these different land uses. And they were really smart too about choosing different sites that had challenging existing criteria. And we'll go over that a little bit. So at the very top, which is not where I'm going to focus, is just a brief description of the control measures implemented. So roadside swales, infiltration areas. This is just a low density residential subdivision. Impervious cover disconnection, which again is a really exciting tool that we can quantify benefits from now. Dry wells, permeable pavement, and other strategies. So that's all detailed in the description on the top. But where I really want to focus in this talk is on the bottom. So you have a locus map on the left that just gives you an idea of where the BMPs are. So the rooftops are shaded. Green is impervious cover disconnection because that rooftop runoff is going into the backyards. So it's impervious cover disconnection is based on a ratio of pervious to impervious area. And we'll go into that a little bit later. And then you have this really informational graphic that tells you the stormwater controls implemented and how they meet the watershed protection standard. So here we have good soils. We have A soils with an infiltration rate of 2.41. And so we're really easily able to meet the watershed protection standard with these distributed controls. And so this will give you a breakdown about how the different areas meet the standards. That's for low density residential subdivisions. For a large commercial property, again, the expectation is overall, you likely are going to have areas that you can provide infiltration, but here VHB introduced two different soil types. So as you dig into the watershed protection standard, it's all based on the amount of contributing impervious cover and the hydraulic soil group that your treatment control is situated within. So in this case, this site is split by design point 1, which has a C soil, so 2.7 inch per hour infiltration rate, and design point 2, which is a D soil. So, here's a good indication of if you do have multiple hydrologic soil groups on site, you can just separate that into design points. And each area would have a different way to calculate the watershed protection standard. If in design point A, as in depicted down in the graph, you can't meet the watershed protection standard because it's D soils and you find the most suitable control is the subsurface gravel wetland, which really has no ability to infiltrate water or permanently retain on-site water, but it does a really good job of managing nitrogen and phosphorus. Then in that design area, the target then shifts from the watershed protection standard to the 60% phosphorus control and the 90, 60, 50. 90% TSS, 60% phosphorus reduction, and 50% nitrogen reduction. And so it details how to incorporate the watershed protection standard, which again includes that cascade of treatment selections on a site that has variable hydrologic soil groups. And then in a large industrial property, again, an example of a range of different controls. And here, the difference being on a large industrial property, maybe it's a area of high potential pollutant load or industrial area that handles a lot of hazardous materials, and we don't want infiltration on this site. That still fits within the framework. And again, we move from a on-site retention standard down to the 90, 60, 50. And so that's detailed here, how that's addressed with these range of stormwater controls, from sand filter with an underdrain to an enhanced bioretention to a permeable pavement on this industrial site. We're going to really hand it to VHB for thinking of multiple ways that would challenge the watershed protection standard. And we know we're just scratching the surface. Hopefully, you'll find ways to challenge the watershed protection standard and then come back to us and say, hey, we ran into this particular issue, and it'll be my pleasure or our pleasure to work on that and work towards a solution. This is an urban institutional property. So here there is B soils. So again, here we're utilizing the watershed protection standard to meet the requirement. And there's different stormwater controls, but overall on-site in this particular area based on the amount of impervious cover and the soil group. We have a target of a 1.5-inch retention on site, and we were able to achieve 1.6. And then I think there's two more examples for hot. What did I skip over? No. No. Sorry about that. Okay, I did skip over. So here's two more examples. High density residential subdivision, a more conventional design. And then there is a high density residential subdivision with a low impact development design. So you have shared driveways, more clustered housing, smaller impervious footprint, whereas and then a large retention infiltration area, as opposed to the standard design that has a little bit more density, more pavement, more roads, but again, it's still able, even in a conventional design, to meet the watershed protections. So these designs are all available, and hopefully will provide guidance, whether you're a reviewer or a designer, to help find ways to economically meet the standard. All right. So I guess I'll hold off and see if anybody has any questions in the chat on those templates before we move on to the actual calculator.
Jamie, there is a comment question in the chat, and I'll read it off. Isn't the permanent protection of intact watershed lands like wetlands, riparian forests, which also serve to provide habitat for living resources, the most cost-effective approach on a per acre basis, even cheaper than LID? And this person says, I would suggest the Watershed Protection Standard with limited focus on stormwater is not broad enough to include all watershed protection activities.
I completely agree. I mean, the Watershed Protection Standard does not replace, nor should it, protective standards around conservation of wetland areas or wetland setbacks, conservation of groundwater protection areas, right? It's not to replace good zoning and planning. And that is really the first order of defense. So I completely agree. Don't fill the wetlands, don't cut down the forests, and preserve those features. They will be the best protection out there. I think what the Watershed Protection Standard does is it includes a balance when there is development, when you do have land use disturbance and you have replacement of forest with built infrastructure. We are trying to, the whole basis is to use these controls to best mitigate that land use change impact. So I'm hoping that's clear. In no way does this stand as a replacement for or allow someone to fill wetlands or build in a very unsmart location like a groundwater protection area. It's really to when there is development, it's to mitigate the impacts of that development to the maximum extent. And it looks like Mark wants to weigh in on that as well.
Yes, thanks, Jamie. And I think that is a really good point. I think as time goes forward, where we have impervious cover disconnection curves to natural buffer areas, forest, the value of the natural systems are quantified and can be used in this thing. I know there's still work to be done to make sure that's part of the menu for people to use. But Maine has done a project recently looking at forest, meadow, and grasslands as buffers and quantified the cumulative benefit. So those things, I think, eventually, as they become more mainstream as a menu option, will help to achieve what the comment or the question was getting at. So I just wanted to mention those impervious cover disconnection curves and the work that is coming out of Maine DEP, I think will help to incentivize what that point is. Thanks.
Yeah, thanks, Jamie and Mark. That's the only question we have in the comment and question in the chat, or in the Q&A box. But just to remind everybody, please do put your questions into the Q&A box, and we'll get to them later.
Great. Okay, so now I want to move into the calculator. And so the calculator is, this is the link on the Watershed Protection Standard Toolkit. It's located on the UNH Stormwater Center site. And it's a little inconvenient, but all of our resources now are in the Scholars Repository. So the benefits of the Scholars Repository is we used to always have to battle people accessing the not the most updated resource. So naturally, we're updating this almost continually. So if someone comes up to us and says, hey, we found a bug or we found something wrong with the calculator, we're always updating it. And now, at least going to the repository, you'll always have access to the most updated tool. The downside is you have to download it every time. So I'll just, why that slide is there. Yeah, so I think what I want to do now is switch over to the calculator. But first, just want to give a basic example of how this would be implemented. So very, very rudimentary. You have some type of land use change, right, where you're putting in this case, a parking lot. We're assuming infiltration rate. So the four things that you really need to know to use the calculator are going to be the area of impervious cover. So that's usually in acres. In this case, what are we looking at? I don't know that it's listed. So you need to know the area of impervious cover. You need to know the soil group. In this case, it's B soil at 1.02 inches per hour. And that you can either take from high intensity survey or like web soil survey, or you can develop that through your geotechnical investigations on site. But we know the contributing area in acres. We know the hydrologic soil group, and then we need to know what type of stormwater control that we're going to be using. And this is taken from the New Hampshire manual, where this is spelled out, just because we've implemented it as guidance. So this is what the calculator looks like. In this example, it's 1 acre of impervious area. We're using a subsurface infiltration practice. We have a hydrologic soil group of 1.02. And then what the calculator is going to do is it's going to, once you input the orange boxes, reflect data inputs that are needed. So I said 4 things. But really, in here, we know 3 things, and we're using the calculator to find the 4th, which is how big, what sizing criteria do I need to actually meet the standards? And again, what's behind this calculator is all the continuously simulated data over 29 years of rainfall record that was developed in the Taunton using I believe, the rainfall data from the TF Green Airport. So is that right, Mark? 29 years or?
For the Taunton, it was TF Green, you're right. And it was a 20-year period was used for that.
20 years.
For Boston, where a lot of the other stuff is 29.
Yeah. All right. So we have 3 inputs, and the calculator is giving us our 4th, which is the size of the system. So what the calculator is reporting is we need 2,178 cubic feet of design storage volume. I'm hoping that DSV is not a new term to you. If it is, we have multiple webinars, again, through the SNEP network that explains the EPA Region 1 performance curves. And this is really the design storage volume, or more realistically, the physical storage capacity, is the horizontal axis for how you engage all the quantitative tools associated with those modeling efforts. So in this case, the design storage volume is just simply telling us how big to make the system. The physical storage capacity is the depth of precipitation treated. It relates the design storage volume to the actual contributing area. So we have 1 acre of impervious going to a B soil where we have a subsurface or surface infiltration system. And we need, in the surface infiltration system, we need 2,178 cubic feet of design storage volume capacity. That relates to the management or on-site retention of a 0.6 inch rain event. So where I said it's roughly equivalent to the 1 inch, we see that with different structural controls in different hydrologic soil groups, it's not always the 1 inch. It's all based on the model. And so this is one of the things that when we're looking at Massachusetts that's implementing something similar, possibly a 1 inch retention standard, or maybe they've been talking about backing off to a 0.8 or a 0.75 inch retention standard. Right? This is still a tall task. What we're doing is harnessing the power of that continuous simulation modeling, which makes the design more variable and more linked to the actual location where you're putting this in. So it's a much more economic and an accurate way of implementing these features. From that design, from this sizing criteria and the control selection, we have these ranges of removal efficiencies. So we're removing about 80% of the volume, 94% of the phosphorus, 97% of the nitrogen, 97% of the TSS. And we also can track zinc and fecal indicator bacteria as well. So you can see the watershed protection standard is really getting the maximum reduction on site of all these other attendant pollutants. Three inputs. You have one unknown, which is the sizing, which is the overall output of this calculator. So it's a little different than a performance calculator, but it's the whole reason of using this calculator is to find the actual size that you need to make your control in order to meet that watershed protection standard. All right. So I just wanted to give you a little information about how does this compare? How does this compare to other regional criteria? And again, we're looking at the Mass DEP 1 inch retention standard, which was in their draft manual of the handbook. They have a static sizing method and a simple dynamic sizing method. So you can see there's not too much difference between the static and dynamic. These are all using NRCS type tools, right? A type 2 or a type 3 rainfall distribution. And I think this is really represents the vast improvement of the watershed protection standard over the more conventional controls that are using a fictitious hydrograph where the majority of the rainfall drops between 11:30 and 12:30 of a 24-hour fictitious day, right? When we track hydrographs over time, we invariably see everything under the sun. Maybe sometimes it fits that type 2 distribution perfectly, but we see everything. We see hydrographs that are heavily first flush weighted, where the majority of rainfall falls at the beginning of the storm. We see some where it falls, light rain, and then everything falls at the end of the storm. We see some constant intensity storm. When we average them all together, it really more matches the rationale the rainfall method than it does the type 2. Anyway, regardless of that, not to get into a speech about hydrology, but we're actually using the real rainfall record. We're modeling real storms that have happened in the past, and we're getting the benefits of the infiltration at a much more dynamic level. And this is what we find when we empirically investigate these things. We find invariably they almost always work more effective and more efficiently, particularly with runoff discard infiltration, than the model ever gives them credit for. If you really want to dig down into the dirty details, we have a master's thesis on our website that was looking at matching empirical results to model results. And what we found is we had to design an underdrain in a infiltration system in order to match the empirical results to the model results. And it was a fictitious underdrain. So we had to design in an underdrain, which was magically discarding water, to actually have the model meet the empirically measured system. All I'm saying is these systems in a dynamic state, the way they operate in the real world, are far more efficient than the model gives them credit for. And I'll leave it at that. So in this case, we have, remember, the Watershed Protection Standard was 2,178. So we're able to really reduce the size of our system compared to a static or even a simple dynamic sizing using NRCS methods with the continuous simulation model. So we're able to reduce the size, save costs, and still meet the relative protection criteria. Our alteration of terrain program in New Hampshire has a groundwater recharge standard that's based on the weighted hydrologic soil group on site, and it's invariably much lower. But they also have very high water quality standards. So if you're in a phosphorus impaired water, you're really being asked to use the limits of the technology with respect to stormwater controls to meet the requirements. So again, while and we're hoping that over time, our alteration of terrain programs move more towards this type of level of protection. So I think with that said, I want to just move over to the calculator real quick. So if you did download it, or when you do, there's a link here, or you can just go to our website, and I will try to see if I can switch my screen here and get the. All right. So someone is going to have to give me a thumbs up if you can see an Excel sheet.
We see it, Jamie.
Okay.
It works.
You never know. Like sometimes you switch screens and you have to stop and reshare. But so I downloaded this. And the first thing if you're downloading this for the first time, you might have some issues with this file does contain macros, and the current versions of Microsoft Excel all have protections against downloading files with macros. So a lot of times you might see this red bar that says security risk. So if that happens, what you have to do is you have to go to where this file is saved. Sometimes it's in your downloads folder, or maybe you've saved it in a different location. Wherever this file is saved, you have to go to the actual file. You have to locate it on your computer. You have to right-click the file and choose properties, and then you have to adjust the properties. This little box will show up. So right-click, go to properties. Under the general tab, there'll be an unblock button. So under general, in the security area, you'll have to click manually to unblock it. That will enable the macros. Since you're downloading this from friendly, trustable source, the University of New Hampshire, I think you can be pretty sure that we're not trying to do anything malicious to the computer. So once you do that, you'll be able to access the calculator. This enable content always comes up. You have to click on that. And now, hopefully, you're ready to go. I should tell you too, this is all the machinery and all the macros and calculations are kind of hidden behind the scenes here. It's just to make the tool easier. But if you want to see the references, they're all in this reference table. So you'll see the different stormwater controls. You'll see the different All the data, again, developed from the Taunton study, that goes into that. We also reference that final report where you can dig into all the details of how this modeling was developed. So we're not creating the modeling, we're just adopting the good science that was already developed through that Taunton study project and trying to implement it in a meaningful way. All right. So now to the calculator. So when you download the calculator, we have a couple of examples already preloaded. You can just replace them, but if you're using this for the first time, they might be useful and demonstrating how to use the tool. So again, this whole tool for quantification of the performance metrics, and even we've linked costs to this as well. Quantification of any of these things that have been developed that are found in Appendix F of the MS4 permit for Mass and New Hampshire. Everything is linked to these four criteria. Here we know 3, and we're trying to use the calculator to find the optimal sizing to meet the standard, which is the 4th and final criteria. So in this case, I need to add the contributing area of impervious cover. We only focus on impervious cover. The short explanation of that is it's because the performance curves only go from 0 to 2 inches. So we're not really looking at anything beyond a 2-inch rainfall event. And when you're looking at precipitation depths that low, it's really only impervious cover that's generating excess precipitation or runoff from those types of events. So you can see here, if I change this to 2 acres, it's going to change my final answer. So you're going to add your contributing area, and then you also have to add your stormwater control. So here you can already see, hopefully, that this is much less structural controls that are available here than in the traditional calculator, because we're only identifying stormwater controls that have an infiltration component. So you're not going to see the gravel wetland here, because there's no, the part of the design is you're developing those in soils that do not infiltrate, or you're lining the system so that you're not infiltrating, right? Because it's a horizontal flow system. So there's no expectation of huge amounts of on-site retention with that system. There, you're going to meet that water quality standard of 50% nitrogen reduction, and that's certainly a system that can get you there. And then finally, you're going to have to add in your infiltration rate in inches per hour. So here, if you look at Appendix F of the Mass MS4 or the New Hampshire MS4, you'll see, I think there was only 6, but through additional modeling, and this is really the power of this tool. Once we do this in a more consistent way, now we have access to the ever increasing science that's available from all the projects that are happening in Region 1. So SNEP is continuing to fund projects. It's funded, as Mark was saying, some additional curves for Maine. It's funded modeling of additional infiltration rates, especially on the low end. So I think previously we stopped at 0.17 inches per hour, but we can go down to 0.1 and 0.05. That's been modeled. We have access to new and improved information. In this case, we're just choosing 0.52. Again, if we change that and maybe your soils are 0.17, you'll see that the design storage volume should have changed. So again, you have 3 different knowns, all creating basically the sizing of your system. So in order to meet the watershed protection standard on this, for this particular sub-drainage area, we need an infiltration, surface infiltration system or bioretention system with no underdrains or elevated ring underdrains to have a design storage volume of 2,541. This is an example of infiltration trench. And the last thing I really want to cover is the impervious cover disconnection, because this is a little bit different. It's not based on it's not based on a design storage volume. It's based on a ratio of pervious area to impervious. So in this case, you have 1 acre of impervious, and what the calculator is telling you is if you're using impervious cover disconnection, you need at least 0.2 acres of pervious area to meet the watershed protection standard. So 1 acre to 0.2 acres, 1 acre of impervious to 0.2 acres of pervious. If we change again this to 2, that number should go up. So now if we're treating 2, we have 0.4, and it's a little bit more detailed than that, but that includes some engineering. For the most part, for impervious cover disconnection, we only count sheet flow. So, there's some limitations, but that's sort of an engineering constraint. If you do have concentrated flow and you're distributing it to a pervious area, in this case, like 0.4 acres of pervious area, you're going to need some type of level spreader or something like that to redistribute it into sheet flow. So the expectation for using impervious cover disconnection is that you have sheet flow. That's the one. So certainly for rooftop disconnection, this is very applicable. So hopefully it's as simple as that. We really welcome and encourage people to use this. And if you break it or you find things that aren't working quite well or things that could be improved, let us know. So we feel like this kind of tool and this type of approach, again, harnesses much more sophisticated and impactful modeling and sort of gets us into a new era of using up-to-date science to design our systems. And when I look across the region, once we stop for questions, I'll also put in the chat, there's a really good talk from Dr. Rob Traver at the Minnesota Stormwater Seminar Series. If you haven't seen it, it's one of the latest talks he gave, and he's developing the manual for Pennsylvania, and they're moving in this direction as well. And it's nothing warms my heart more than to have different regions of the country come up with similar solutions. And Dr. Traver is one of the godfathers of stormwater researchers at Villanova, and has been looking into this for decades. And it's just nice to know that we're kind of landing in a similar spot using this on-site retention standard as a way to better control our stormwater and to better manage our stormwater. So I'll drop that into the chat, and then I'll stop sharing now for questions and answers, hopefully.
Thanks, Jamie. And yeah, while you're doing that, I will pull up the Q&A box and welcome others to put your questions into that Q&A box, and we'll do our best to get to them. Yeah, and Jamie, let me know when you're ready.
I'm ready.
Okay, awesome. The first question is, have any municipalities or state agencies adopted the Watershed Protection Standard as regulation, or do you know that any that plan to?
I think we're working on that now, and certainly as we look into the future, we've been working with 2 towns, North Kingston in Rhode Island and Mansfield in Massachusetts, and sort of providing some supplemental data and research to help them make decisions to make a decision to adopt. We haven't seen this adopted by a municipality yet, so we're always on the hunt for someone who's willing to do it. We have seen adoption of very high stormwater control standards. I would say, certainly in the Charles River watershed, there's lots of really very progressive regulations. I think the town of Watertown, Mass, has a retention of 100-year storm. So we're talking about, relatively speaking, the 0.6 to maybe 1.7 inch rainfall event on-site retention based on hydraulic soil groups. They have a standard of retaining the 100-year storm on site. So that is much more than we're talking about. But again, that's highly developed area, very vulnerable infrastructure, and they're looking at that as a climate resiliency or building a resiliency in the watershed.
Our next question is, do you have the links to the research regarding the infiltration in areas with rates as low as 0.05 and 0.1 inch per hour?
Yes, I know we do. We're working on a document right now that summarizes all the literature. But Mark, do you know specifically where that comes from?
Uh, um, I had collected a bunch of references of research done on measuring infiltration performance in very low permeable soils. Um, and I'd have to go dig through and see if I can find those. I know New York City documented. I know you documented at the Stormwater Center, Jamie, in I think that some of your masters, some of the one of your students' work. So I think there's a fair amount of literature out there demonstrating that the systems in these very low permeable soils perform much better than expected. The two numbers, the 0.05 and the 0.1, were just brackets for low permeable soils. They weren't taken from a specific study. They were just estimating those performances should the infiltration rate be that. So I can look for, there's a bunch. If you Google it, you can find them. I remember I had 5 to 10 studies that documenting, confirming that performance was much higher than expected. And I just say the performance is evaluated on a cumulative basis of all the rainfall, not design storm. Because when you go to the design storm, then that high intensity design storm, the system's low permeable soils will not perform well. They need time to drain. So I just mention all that.
Yeah, and I'll put a link in. I know we have we were trying to update all the performance curves that are available because in the science of performance curve development, the development of these curves is outpacing the ability to get them in a permit. And we feel that that's fine as long as they're documented. So what I'm putting in the chat now is our recently updated fact sheets on the performance curves that documents everything that's in the calculator. And I believe it also has the references from where the data comes from. At least that was the intention of putting this together. So I just put the first link I dropped was Rob Traver's speech at the University of Minnesota Cold Climate Stormwater Center of Excellence Stormwater Seminar Series. That is a great show. I highly encourage you to look at it. And then the next link I dropped was the updated performance curves. So the idea is, as the science improves, we're hoping to also include the main curves as well. So the impervious cover disconnection curves that Maine developed. In the IC disconnection curves that are in our calculator or in the performance curves already, we assume it's disconnecting to a typical undisturbed area, whereas the main curves assume that disconnection is into, as Mark said, a wooded or meadow type land use. So it improves the curves for those types of impervious cover disconnections. So as we develop, as long as we're doing this in a consistent way, we're going to continue to just make these calculation tools more robust and more reflective of the latest science.
Thanks, Jamie and Mark. The next question is, design storage volume is a retained volume, not an overall volume of the system, like the volume below any outlet from a system, correct?
Design storage volume is a characteristic of the structural control. So the way you calculate it is you have length, width, depth of the area. So a ponding area, you have the length, width, depth, and the porosity. So a ponding area, which most systems will have or controls will implement, will be a porosity of 1. So length times width times depth times porosity. In the soil, it's a length, width, depth times porosity of typically 0.2. And in a stone reservoir, it's a length, width, depth times porosity of like 0.4. And what we have done, and it's certainly in New Hampshire, and this is all founded in the empirical research, there's a big debate out there. So if you talk to my counterpart at the University of Minnesota, Andy Erickson, he has whole presentations about the unnecessity of underdrains. We like underdrains. I particularly like underdrains because we're often installing these in the built environment, and it's a belts and suspenders. So it's a very cheap way to eliminate potential flooding of adjacent infrastructure. However, we have found that if we elevate the perforated underdrains within the system, unsaturated flow conditions dominate the way these systems process water. We assume saturated flow conditions, which invariably almost never happen. So we rarely see saturated zones, and it's one of the reasons why we have to make up underdrains in these systems to have the model data mimic the empirical data. So if we elevate the underdrains within the stone reservoir, then and unsaturated conditions are dominating, then those underdrains are really never being accessed. Only in the storms that are way beyond the design storm are they going to be accessed. So we've had this debate back and forth. Underdrains are evil, yes, but they're really cheap. They're really cheap belts and suspenders, prevention of flooding. And if I elevate them, then effectively my system is performing as if it has no underdrain. So that's why we say if you're doing a bioretention systems with elevated underdrains, you're modeling it as a surface infiltration system. Done.
I think we have time for at least one more question. Are there provisions in the retention standards for allowing technologies that augment poor draining soils? For example, there are permanent structural practices that allow DC soils to perform like AB soils.
Currently, I think the answer is no. But again, what I really like about this type of consistency is that is something that is a new and innovative way to better manage stormwater. Let's study it and let's develop a curve for it. And that's what we've been doing. We developed a curve for high flow rate media systems. So if you're a manufactured treatment device provider or you're implementing manufactured treatment devices within the built environment, these high flow rate style systems, you don't necessarily have a curve that you can account for. But we just completed a study that was funded through EPA Region 1 where we developed a representative curve. So now hopefully it'll be adopted in the new permit, and we'll have a way to account for quantify manufactured treatment devices. So if these soil amendments are really something cool, then let's work on it, develop the standards, and develop a curve for it.
We do have time for
Jamie,
this.
Leah, could I just add to that? That's a really good. This is a great discussion about soil augmentation, improving hydrologic performance, because in the original Charles River residual designation done back 2010, in that permit, we had done performance curve modeling for the event that Scott is describing there of upgrading the soils. And while, what does that mean? But what it does mean, it highlights the potential benefit of doing that. So Jamie's exactly right about, let's figure out and have some design standards for that. But the performance is significant. Obviously, the performance would be significant. So it's definitely putting out the results first to get people to kind of fill in the technical details is kind of the way it goes sometimes. Thanks.
And yeah, thank you, Jamie and Mark, for being here. I know we're wrapping up on time. I just wanted to let everyone know I dropped another webinar training opportunity in the chat that will feature Jamie as well as another network run by the New England Environmental Finance Center. So please check that out if you have a chance. And just want to remind everybody that the recording will be available in the coming days, as well as links to all these great resources. Thank you, Mark and Jamie, for putting them into the chat. And then I'll also make sure that any that were on the screen will also be shared with you all. So any final words from Jamie and Mark before we close out today's webinar?
No, just thank you. Use the calculator and let us know how we can improve it.
Great. Thank you, everybody. Bye.